Hello, good afternoon. I hope you can all hear us well. Welcome to this webinar done here at ECMWF to celebrate the launch of the consolidation phase of the year of polar prediction, and perhaps some of you were able to see already this morning a more general webinar by Thomas Jung, who chairs the polar prediction project of WMO, about YOPP in general and what we are going to do in the consolidation phase. And if you missed that, you can still watch it on the YOPP YouTube channel. Today, I'm not going to give an overview of the YOPP in general and on the consolidation phase, assuming that you have all seen Thomas' talk. But what I will do is talk about what are the challenges, some of the challenges that we need to overcome if we want to improve weather prediction, but also climate monitoring in polar regions and in particular in the Arctic. And I will say how YOPP, the efforts made in YOPP, both in the core phase, which is just ending now, and in the consolidation phase, contribute to overcome these challenges and thereby to improve prediction and climate monitoring of the Arctic. So, let me start by reminding you that weather forecasts have experienced a quiet revolution over the past decades. What we mean by that? Well, weather forecasts have improved markedly, and this graphic here shows the evolution of the anomaly correlation of the geopotential height at 500 hectopascal for the north hemisphere and the thick line, and the southern hemisphere for the thin line, for forecasts 3 days ahead, 5 days ahead, 7 days ahead, or 10 days ahead, that were made with the here at the European Center for Medium Range Weather Forecasts from 1983 to 2017. And if you just look at this arrow here, what you basically see that the anomaly correlation in this key metric of NWP skill reaches 80% now, a level of 80% 7 days ahead for forecasts done nowadays, while this was the case for forecasts made 5 days ahead 20 years ago. Otherwise said, weather forecasts 7 days ahead are as accurate as weather forecasts 5 days ahead were 20 years ago. And why have weather forecasts have improved at this marked pace? Well, it's because of combined advances in key ingredients of numerical weather prediction. Assimilation methods, in the use of observations, and of course due to enhanced supercomputing facilities. And I really want to emphasize this from the start, because it's important to keep in mind that if we want to improve predictions, not only in the Arctic but also elsewhere, it's important to improve all the components of the NWP systems in parallel. And this improving the NWP systems is important not only for weather forecasts, but also for modern reanalysis, because modern reanalysis such as the well-known ERA interim or ERA 5, which is produced here at the European Center by the Copernicus Climate Change Service, are great, and which nowadays have a resolution of 32 kilometers globally and span 37 levels on the vertical. These reanalyses are really a great tool for climate monitoring of the Arctic. And in this bottom plot here, you see the linear trends in 2-meter temperature since 1979 to 2017, with this pronounced warming of the Arctic. And these reanalyses as well are getting better nowadays because the NWP systems have got better. And what this figure here on the left shows you, it shows you that some of the key events for Arctic regions, the southern stratospheric warming events in the stratosphere, are much better reproduced in ERA 5 in red than in ERA interim. This particular figure showing you the difference between the microwave radiances as observed by one of the satellite channels peaking at 5 hectopascal and as deduced from the temperature fields of ERA 5 OIRA interim. And you can see that the distance, the difference between observations and the model fields is smaller, which means that these events are much better reproduced. So enhancing and improving our NWP systems helps not only for weather predictions, but also for climate monitoring. Now, coming to the weather forecasts from in the Arctic at their quality, I come back to my slide of this key NWP metric, which is the anomaly correlation of the geopotential height at 500 hectopascal. This is for forecasts done 5 days ahead, forecasts which were made since the 1990s till today, again, 2018. And the red curve is the curve I showed earlier for the North Hemisphere, while the blue curve shows you the anomaly correlation for the Arctic. And you can immediately see that whether, even if the Arctic forecasts have improved over time, their skill remains markedly lower. And this can be due, of course, to the fact that perhaps there is less predictability in the Arctic, and this is particularly true during the summer season. You can see this here, the gap between the two curves is more marked during summers. You can also see in these plots here, which show the root mean square error of the geopotential height at 500 hectopascal, again for this forecast done nowadays 5 days ahead for a winter and summer season. And you see that the root mean square errors are bigger in the Arctic than in mid-latitudes, is particularly during summer. So the difference between these two curves is in part due to the fact that the Arctic is less predictable in summer, but it's also due to the fact that the challenges, and I'm coming to these challenges in the following slides, are larger in the Arctic and polar regions in general compared to the mid-latitudes, and these challenges are due again to all components of NWP systems, namely to the representation of physical processes, the coupling between the different components of the Earth system, the use of observations, the data assimilation techniques used to create the initial conditions for the forecast, and I'll cover that as well in a bit, and challenges related to the representation of uncertainty in ensemble predictions. So in the next slides, what I will do is tell you how YOPP, give a few examples of these challenges and tell you how YOPP is helping addressing them. And what is really important to point out, and this is a good lesson for future programs related to other other aspects of the Earth system or predictability or prediction, is that why the year of polar prediction and the polar prediction in general project of WMO is successful in our view is because it has had from the beginning a very strong modeling plan. So that means it brings together observationalists with modelers, and they have a common plan of how to address the different challenges. YOPP, as you can see, this modeling plan has many components. It involves data sets, it involves modeling and process studies, it involves studies related to observing system design, it involves verification, and it has involves targeted diagnostics. And this is really one of the strengths of YOPP compared to previous initiatives. So let me give you a few examples of these challenges, starting by the modeling challenges. And this nice figure from a recent paper by Pitan and colleagues gives an example of one of the hardest things to capture in the Arctic, which is the Arctic air mass transformation. What does that mean? Well, think of these moist air intrusions which bring warmer and moister air from the mid-latitudes in the Arctic regions, and the air mass suffers a transformation while it is advected over colder and colder surfaces. It cools, clouds form, then these clouds rain or snow, and then they disappear gradually, and then the air mass becomes very, very cold, especially near to the surface due to radiative cooling near the surface. And Pitan and colleagues have shown that the models really have a very hard time to reproduce these two states, this cloudy state and this clear state, which have very different characteristics in terms of their effect on the Earth's radiation budget at the surface. The cloudy state has almost a zero net effect on the long wave radiation, where the clear state has this pronounced radiative cooling in the lack of clouds. And the models have a hard time doing this transformation from one type of air mass to another due to the fact that they really struggle with many of the processes involved, which are stable boundary layers. You may know that these are very hard to model, mixed phase clouds and the partition between ice and liquid, ice-sea atmosphere coupling, but also sea ice, snow of sea ice, and again and also the wide range of scales involved, from these large scale intrusions which span a few thousand of kilometers to very small scale processes, like for example entrainment or partition within this which in these mixed phase clouds, which often have supercool liquid water. Another challenge, another modeling challenge is the coupling. The coupling between the atmosphere, the sea ice, the snow, and the ocean, which are all involved in the Arctic. And whether climate models have been using already ice, sea ice, and ocean components for a long time, these are relatively new in NWP. In the ECMWF ensemble system, these have been used only in the last few years. And the coupling to these new components comes with specific challenges in NWP because in NWP, compared to climate, initialization and the creation of initial conditions, or the best guess from which the forecast starts, is really important. But also because the temporal and spatial scales involved are much smaller. The grid box size of today's global NWP models, like the ECMWF model, is of the order of 9 kilometers, while global climate models have scales of the order of 100 kilometers. So what does YOPP do to address these coupled model challenges? Well, on one side, it makes new observations in the core phase of the coupled system, both in the atmosphere, through the snow and sea ice, and in the ocean, but it also sets up novel tools for better diagnosing what are the problems are. It, for example, in the framework of Applicate, one of the Horizon 2020 projects, which supports very strongly the year of polar prediction, we had set up this novel coupled single column diagnostic, novel single column, which involves the atmosphere, the snow and sea ice, and the ocean, which can be really used using observations done in the core phase of YOPP, and which will be done in this big new observational effort called Mosaic, where a ship is going to, the polar stern is going to be frozen in the ice. It will drift around with the ice for 1 year. So these observations can be used together with the single column model to understand what are the challenges and how we should better couple these different system components. Another thing what YOPP is doing is making available to the community, research community, for free data sets, forecasting data sets, either providing process tendencies, which are normally not provided. This is the case for the YOPP data set we are providing here at ECMWF for the duration of YOPP. We are making available the control of our coupled forecasts for 15 days at an 18-kilometer global resolution. And we are providing these tendencies from the physical processes, and I'll come back to that in a second, and Environment Canada, and you'll hear this more tomorrow probably from our colleague from Environment Canada, Greg Smith. I have been doing these unprecedentedly high simulations at 3 kilometers over the Arctic, and they're also providing global simulations at 24-kilometer resolutions, all coupled with the ocean. So why is it important to have these data sets, to make them available to the research community? Well, because in parallel, and let me just, and this is just an example of the YOPP ECMWF tendencies, so you can plot yourself the tendencies from the different physical parameterization and compare what happens in the Arctic, what happens in the mid-latitudes. And moreover, one can combine, and we hope that the community is going to pick up this data set and is going to pick up the other very nice initiative that is done in the framework of YOPP, which is to put together observations from these observational supersites, which encompass a large number of observations at various sites through the Arctic. So this is the YOPP site MIP initiative, where in particular IASOA at NOAA, they are producing merge observatory data file in a common format. As you know, the observations can come in different formats, and it's very important to put them in the common format so that people in the research community take these data sets, the observations on one side and the models on one side, and compare them, and they do process-based evaluation in order to understand what are the modeling biases, how are the models performing in terms of process representation in the Arctic, and how we can make them better, what they are doing wrong, how can we improve them. And that's exactly one of the main purposes, what we want to do in the consolidation phase. And this is a nice example of work that we have done here at ECMWF in the framework of the Horizon 2020 project Applicate, where we used observations made at the Sodankila site in Finland to look at why our model is too warm near the surface. Here you just see a comparison of 2-meter temperature from our model, current version of our operational model with observations, and you can see that if we, and this shows you, the red shows you a warm bias over several degrees, and you see that if we would replace the representation of the current snow model, which is it contains one single bulk layer of snow with a multi-layer snow, we reduce this bias. Blue here means a reduction in this warm bias throughout the high latitudes. And the supersite data at Sodankila allow us to have a look both in the lower atmosphere through the snowpack and within the soil. And in blue here you see the observations. In green you see our current model, and in red you see our future model. So you can see that this multi-layer snow allows to reduce this near surface temperature biases, but it also allows to better capture this strong gradient within the snowpack. Another example of how observations, this time made in the winter special observing period, which was last year in January and February, also are already used to understand model biases in the framework of various projects. And that's why it's so important. I want to come back to this point I was making at the beginning. It's really important that people who are doing the observations work from the beginning with the people, the modelers, because they can all use very quickly the observations, and they can try to understand what is the source of biases. And what you see here are results from a recent paper by Morten Koslow and colleagues, both in the framework of Applicate and in a framework of Alertness, a Norwegian project, which shows that two of the regional models, our ROM Arctic and our ROM, when we compare the short-range forecast, 30-hour forecasts, with the observations for very cold situations, you can see here in the observations is -40, -20 to -20. The models perform pretty well. The match between the model and the observation is quite good in our ROM Arctic. It's not that good in our ROM, and it's even worse in the ECMWF IFS, which has a much lower resolution as well, and it's also a global model. But by doing this type of targeted verification, we learn that in this observed calm winds, told us which of the models are doing better and which are doing worse, and now we are looking into why. So these are some of the ways YOPP is contributing to understand and overcome problems in the models, but it's not, as I was saying at the beginning, doing better forecast is not only about the model, it's also about the initialization of the forecasts through data assimilation techniques. And the accuracy of the initial conditions from which the forecasts start is really one of the key factors in skill of the weather forecast over time scales of a few days to a few months. So comprehensive data assimilation systems are used to blend the observations depicted in this picture here by these dots with the short-range forecasts over a time window which in the ECMWF system taken here as an example is of 12 hours. So the observations are blended, optimally blended with the forecast depicted in blue here to produce an optimal and best guess of the atmospheric state from which is called the analysis, from which then the ensemble forecasts are starting. So what happens is that the observations are used to create increments in prognostic variables such as temperature, winds, humidity, etc. So to correct the forecast errors. The quality of an analysis depends both on observations, on the model, but also on the way the observations are used, either through observation operators to project them into model space, or but also through the weighting which is done, which is given to the observations and to the models when producing this blend, this analysis. And we know that the observations and the models are not perfect, but as long as the observations and the background forecast uncertainty are properly specified, we should be able to produce an optimal analysis. And then as long as the initial condition and model uncertainty are properly specified, we should produce reliable ensemble forecasts. So one thing we have, and so far we knew very little of how optimal this representation of uncertainty is, especially in the short-range forecast used in the ensemble of data assimilation to create the initial conditions. We knew very little how this compares in the Arctic with extratropical regions. So another piece of work we did here at ECMWF in the framework of Applicate was to look at the skill of the short-range forecast versus observations and to compare that with the ensemble spread. And if the ensemble is reliable, we would expect that the skill matches the spread, and this is indeed true if you look here for the northern hemisphere extratropics, or for the northern hemisphere and southern hemisphere extratropics, but it's quite different if you look at the North Hemisphere pole and South Hemisphere pole, particularly, for example, for the winter hemisphere in December, January, February. You can see that the spread is smaller than the skill. That means the ensemble spread is too small in the lower troposphere. So what does this mean in terms of producing the analysis? Well, it simply means that both in the lower troposphere and the upper stratosphere, which I'm not showing you here, the adjustments the observations can make to the short-range forecast in the Arctic during the assimilation is now limited. So even if we have observations, then we don't necessarily make the best use of them. And the aim would be in the consolidation phase to improve on this uncertainty representation, and thereby on the quality of the analysis. And finally, there are also challenges in the use of observations. And perhaps when you think of the Arctic, you all think, oh, there are no observations in the Arctic. And this is true for sure, mostly in terms of conventional observations. If you think of radiosones and number of, and surface pressure observations, and this just shows the number of radiosones and surface pressure observations which are assimilated at ECMW, which are assimilated in ECMWF for a recent summer and winter period. And you can see that especially the central Arctic is quite void of observations. So for sure, we have less conventional data above 70 north than in the northern mid-latitudes, but also there are larger model errors due to this to the fact that is more difficult to represent stable boundary layers and snow and sea ice. And also, as I shown on the previous slide, we probably give too much confidence to the model in the lower troposphere when using these observations. And this is another piece of work we have done in Applicate here at ECMWF, and there is a technical memo which describes that if you are interested. However, when you think of the pole and how many observations we have, it's certainly not true that the Arctic is void in terms of satellite observations. In fact, in terms of satellite observations, the number of, and the top plots here show you the number of observations assimilated from just one of the sway microwave channels, which peaks in the middle troposphere between 500 and 700 hectopascal. And you can see that there is more yellow in the Arctic. That means higher numbers in the Arctic than in the mid-latitude. So in fact, in terms of satellite observations, we have better coverage from polar orbiting satellites than anywhere else in the world. However, we also looked at this in this recent piece of work here at ECMWF. There are more challenges with the use of these observations because model errors are bigger. So the distance between the observations and the forecasts, which is shown in this bottom plot, you can see particularly in winter that what we call these departures between the observation and the forecast are higher over regions where we know there is sea ice and snow there, and that's due to model errors being larger, but also due to errors that we make in the radiative transfer modeling when putting the observations from observation space radiances into model space, that's temperature and humidity, for example. And this radiative modeling is particularly tricky over snow and sea ice because then it's complicated to represent the surface emissivity. And why is this important? Well, because if these differences are too big, the data is simply rejected during the assimilation process. So it means some of this data, not all of it, but some of it, it's not used even if we have it. So to summarize, we have challenges in modeling, we have challenges in the data assimilation techniques, and we have challenges in the use of observations. And we, in the core phase so far, and in particular in the framework of Applicate, we have looked at some of these challenges. Another thing we have also looked, and this, if you would have seen Thomas talk this morning, is another concerted effort in YOPP, which consists in trying to understand better what's the role of the Arctic observations that we use in the quality of the weather forecasts, both in the Arctic but also in the mid-latitudes. And to do that, we have us at ECMWF, but also colleagues that you will see at many other centers, in particular Canada, DWD, FMI, have done a concerted efforts by doing extensive numerical experimentation, which is very expensive and which we normally don't do, and is in this so-called observing system experiments, in which we simply remove the observations from different regions, in this case in the Arctic, and then we analyze the increasing forecast error when we remove these observations, because we want to understand how much observations contribute to the increase in forecast skill. So it's the first time recently in the framework of YOPP and Applicate that this exercise has been done for the Arctic. So what we have done and the South Hemisphere, in fact, we have run 3 months of winter covering the YOPP SOP and 3 months of summer, and in fact we did it for 2 summers, the summer 2016 and the most recent summer, which includes the YOPP, the second YOPP special observing periods, and we removed different observation types, both north of 60 north and south of 60 south, and then we and this is just a slide, a summary of the multi-center observing system experiments. And this is just for you to see that we've done these experiments at quite high resolution, not operational resolution, because that would be extremely expensive, but at very high resolution, still 25 kilometers for ECMWF, 39 kilometers for Canada, 13 kilometers for DWD. And we did this for several periods, and we removed many types of observations, either satellite or conventional observations, and we split that in different ways. And also colleagues at Met Norway and FMI, in the framework of a project called Alertness in particular, they are also doing such data assimilation simulations, but with the regional systems to understand the impact of Arctic observations through data assimilation, but through also through laterally boundary conditions. So what have we learned from this quite expensive exercise when you think about it? Well, this exercise was very important because it allowed us to really measure for the first time how much the forecast skill would be degraded, both at the North Pole. We didn't focus so far on the Southern Hemisphere, but the runs are there and could be looked at if people are interested. So we looked at how much the forecast skill, not only in the short range, but really in the medium range, is degraded both at the North Pole and in the northern mid-latitudes. So what this graphic shows you, it shows you for a summer period at the top and a winter period at the bottom, the increase in the standard deviation of the forecast error in the latitude band from 60 to 90 north and in the latitude band from 20 to 60 north, otherwise said kind of north of the 60 north, and in the mid latitudes for different observation types. So what you can see is how much the forecast error increases if we remove the microwave observations. This is about 10%. Day 3, these are results for day 3 of our 10-day forecast performed with the ECMWF system. It's about 10% if we remove the microwave observations in the Arctic, and it's still about 3–4% in the mid-latitude, still at day 3. And then the microwave, in summer, the microwave impact is followed by the conventional infrared signal, GPSRO, and the atmospheric motion vectors. In winter, you can see the impact is less. You can see that these bars are shorter. There is a less of a degradation, less increase in forecast error. But you can also see that the ranking is different. You can see that while in summer the microwave observations are the most important, in winter the conventional observations play the biggest role. And that is due to the fact mainly that probably because we don't do that good of a job when we assimilate the microwave observations nowadays, in particularly over snow and sea ice. This is this point I was talking about earlier. So, and these results are, even if they are a little bit different, at least the ranking comes similar from colleagues in Canada. So from this we learn, we could really measure how much current observations play over a role. Also, what observation matter most and which season. And this is important also for guiding the design of future observing systems. But it's also important in terms of understanding Artitude to mid-latitude linkages, which is another aspect which is very much in the focus of YOPP, because YOPP aims to improve environmental predictions not only in the Arctic but also beyond through linkages between the Arctic and the mid-latitudes. And this is an example as well of, again, applied work done here at ECMWF, a recent paper by Johnny Day et al. Submitted to QJ. So what this shows you is that when we remove the conventional observations during winter, we increase quite a lot at day 1 the forecast error, the root mean square error of the geopotential height, again at 500 hectopascal in the sort of Arctic circle at day 1. But if we look at longer range at day 4, we can see that this effect propagates, and we also deteriorate the forecasts over North Asia. And if we try to understand better to which conditions this is due, what we figured out, and this is what this plot shows you, in fact, the difference between each of the observing system experiments in which we remove one of the observation types, the in situ, the microwave, the infrared observations, and the control. And you can see these spikes. This means really that on certain days, this is the time here, the quality of the forecast at day 4 in this box is degraded. And if we look at what weather regime predominates in when we see these spikes, we see that almost all of them appear in regions of Scandinavian blocking, and I'll show that in a second. So what we learned from this is that removing the in situ observations or satellite observations in the Arctic from the data assimilation system used at ECMWF, used to create the initial conditions of the forecast, this deteriorates the mid-latitude synoptic forecast skill in the medium range, particularly during episodes of Scandinavian blocking. And this plot is just showing the circulation type in these particular conditions, where removing the observations in the Arctic deteriorate the forecasts in this region here. So you can, this is again the anomaly of geopotential height at 500 hectopascal. You can see this pronounced blocking. So these are regimes which enhance baroclinicity here in the North Atlantic sector, but also situation in which through a planetary wave train, these errors here obtained when removing the observations in the Arctic can propagate into the mid-latitudes. And even more interestingly, I quite like to show this plot because it shows that these situations, these blocking situations, are the situations in which we have this warm intrusions. This shows 2-meter temperature for one particular day in this regime. You can see this warm and moist air intrusion, this plot showing the total column water into the Arctic. So if you remember what I was saying at the beginning, these are really the situations that model struggling. So if we would be to improve the observational coverage in regions of high error growth in the European Arctic during the Scandinavian block events, we should improve the forecast errors not only in the Arctic but also downstream over North Asia. So this brings me to my summary slide. So what I try to give you an overview of the specific challenges in the Arctic and in polar regions in general, which are coupled model errors, which are larger, and the range of scales involved is wider as well. We also know that the Arctic is sparse in terms of conventional observations, but is very rich in terms of satellite observations, but we don't necessarily use these observations probably as best as we could, in particularly over snow and sea ice. And the background error representation and uncertainty representation in ensemble systems and data assimilation system is more challenging as well. So what have we achieved so far in YOPP? What would be some of my top things that I think we achieved would be that we really managed to put together modeling and observation data sets, which are really key if we want to better understand why the models are wrong and how we should improve them. We managed to have a better understanding of the sources of errors, but also of the usage of Arctic observations, and we managed to demonstrate the importance of Arctic observations for mid-latitude predictive skill in operational NWP. But also among the different centers, there have been already improvements to different components of NWP systems, and there has been a concerted effort in the YOPP consolidation phase towards, I mean, the main aim of YOPP is, as Thomas was pointing out this morning, is really to achieve improved environmental prediction capabilities for polar regions and beyond. And what we hope to achieve during the YOPP consolidation phase is really to enhance our coupled modeling, to improve our data assimilation methods, and to have a more effective use of observations in numerical weather prediction systems. So that is all I had. If you have any questions, I'm happy to answer them. Thank you. Yes, I will answer. So Fujito is asking, is there a clearer view of the Arctic tropics interaction? In the particular work I've been showing here, done here at ECMWF with the observing system experiments, we haven't seen anything yet between Arctic and tropics, but another component, and I invite you to watch Thomas' webinar this morning, is the so-called PAMIP, this polar amplification model intercomparison, where it's more on climate timescale, and there the linkages are explored much more in details. I would invite you to watch Thomas' presentation, and hopefully that will give an answer to this question. If you have any other questions, please type them in on the chat on the side. Yes, ECMWF is in continuous use with our users of the forecast. We continuously receive questions from our users, and there is an email address, which I think it's support at ECM, user_support at ECMWF, where our users can send us continuous feedback. So I don't know if that answers your question. And we are always happy to receive questions or respond queries about our forecasts. So if you have any questions related to our forecast, please do drop us a line, have a look on our website at our, what are the support, the mechanism to contact our user support. Okay, thank you very much for your attention. And if you are free, please do watch as well the third seminar webinar in this series by Greg Smith tomorrow at 15 UTC, the same time.